All right, everybody. Welcome to the next lesson here in the series about computer memory for coders. So, what I'm going to show you guys this time, and gals, is an actual demonstration of what I was talking about before. So, my last video, I didn't do any screen recording. I just talked face to face. But this video, I'm actually going to show you proof and evidence of how all of this is working. And one of the things that I mentioned was that how your program that you write as a programmer, like if you're programming in a higher level language such as C, which is funny because a lot of people don't even consider C to be a high level language anymore, but believe it or not, it actually is. But if you're programming in C, C++, C Sharp, uh, even like JavaScript, although there's other steps in between an interpreted program, which is what or an interpreted language like JavaScript, but still, all of these languages eventually get turned into um, machine code instructions, and assembly language is a way to visualize that. So I'm gonna show you all this in just a second. And there's a reason why I'm going to show you this stuff, and it's because it's going to teach you at the very core how memory works with the computer, and that's what this series is about. Okay, so as you can see here, I have a very simple program because the idea here is not to be too complicated, but I do want to demonstrate a few things. So that's why I have like this constant global constant out here, which is outside of any function. And then inside of main, I have a static or a local variable here, which is I, which is going to be used as the increment variable in this while loop. So I didn't use a for loop. I chose to use a while loop. That was just a little decision on my part. But for loops and while loops are basically the same thing anyway. So as you can see here, what this program does is it starts at 55 and it goes all the way to 105, but it only prints numbers out which are multiples of 5. So if you're not familiar with C at all, like honestly, everything else in this program should be understandable to you if you do any coding pretty much. But the only thing that might be a little bit confusing is this line right here and this line right here. And all this line right here does is it prints I, and then it prints, or it writes I on its own line. So this backslash n is basically like hitting return. So long story short, every single one of these numbers will be on its own line. So in C sharp, that would be like console.writeLine, and I can't remember Java. It's like system out write line or something like that. Um, in C++, it's C out, and it's a little more similar to this, but anyways, that's all that does right there. And then return exit success is basically just telling the operating system that it's giving us a return code from the program. So this will tell this will give the return code that the program exited properly, versus if it crashed or something like that. So this is just exiting the program. So um, now that's a very simple program, and I ran it right here just to show you exactly what's going on here, right? So 55, 60, 65, 70, 75, 80, 85, 90, 95, 100, 105. So this is actually printing 11 different um, numbers here. And the reason why is because I chose to put less than or equals to right here so that it actually prints the 105, which, by the way, you got to be careful with this. This is called a one-off error, where this happens a lot with programmers, where like they compare it, they call it a fence post error sometimes too, because it's like if you want to make 10 lengths of fence, let's say you're building a fence around your house or something, and you need to make 10 lengths to get to cover one side. Well, you actually need 11 fence posts, but so if you accidentally don't include the 11th fence post, or you just say like for 0 to 9, and then or for I equals 0, I is less than 9, or I is less than 10, I mean, and then I plus plus, you're actually you're gonna be one short basically. So, anyways, that was a little aside right there. But that's something that sometimes allows hackers and crackers to actually exploit your program. So, just FYI on that. So, what I'm going to do now is I've shown you the program. You see what the program does, and it also prints out "Thanks for playing, goodbye." And there's a reason why I did this. I'll show you in a second. So now what we're going to do is we're going to disassemble the program. So we're actually going to look at the machine code instructions, the opcodes that I was talking about in my previous videos. We're going to look at those to see what this program actually becomes to the computer, because the computer doesn't actually see any of this at all. Like it's not even remotely close to this. It's very interesting, but it is very eye-opening, and it will also help you understand memory. So here we go. So I'm going to take the program, which is called demo.exec, right? And I'm going to drag it onto this program here now. This is called IDA Pro free version. It is free, and you can go, I'll put the link in the description, but it's a really cool program, and if you do any reverse engineering or like malware analysis or exploit development and stuff like this, then you'll be very familiar with this thing already. But that's all it does is it takes an executable machine code program and it breaks it up into somewhat human readable assembly, which we call this a disassembly, right? But don't get bogged down by all these details, and like this is extremely overwhelming. This, that's why I just got rid of that toolbar. Like that toolbar even drives me nuts, to be honest. But so I don't want you to like worry about all this stuff and what all this stuff does everywhere, because I'm going to show you a few specific things for a specific purpose, right? So, so this is interesting, isn't it? All right. So these are functions right here that are being called. I don't even have a function called setAppType in my code. Okay, like check this out. There's no setAppType in here. And so that shows you right there, like I was saying, that the code, there's a lot more code that ends up going to the computer than what we program, even in a low-level language like C. So I'm going to hit spacebar here and take a look at this. Like, look at all of this stuff that's in this program. Right? Yeah, like that's literally just to run to do. It's literally just to do this right here. Okay. So like if that doesn't show you what I was talking about before about how the program's actually much different from how you programmed it, then I don't know what will. So now, so we got that point, right? Now let me actually go to the part that I did program, and it can be actually hard to find because you got all these different other functions here, and a lot of these functions that we're seeing here where it says call, they're functions that the compiler put in and the operating system uses to set up the memory space and the memory addressing and all this stuff for our program to run. And some of these things also, they actually do things like print the text to the screen, because our program itself doesn't have code that tells the operating system to tell the video driver to tell the screen where the pixels are to print out the stuff that we printed right here, and that stuff has to get done. Like this gets printed to the screen because the screen is told put 55 with these pixels in this location and all that kind of stuff. So, some of this code has to do with how that stuff is how our program is making those calls to the operating system to get that stuff done, right? Okay, so let's actually find where our program actually is. Now, so one way we can do this, that's why I put that string in there. One quick way to do this is to look for that string. So this IDA program is amazingly powerful, and it gives us all the strings that are in the memory of this program. Or that will be loaded in memory. The program itself isn't actually running. It's on disk. But IDA can go through the program and find out where the string is even on the disk. So I'm gonna actually double click this because you can see the thanks for playing goodbye here. And that takes us to the memory for our program. Okay, so this is like the data. This is the data area of the program where, see, it's called R data. This is what we call read-only data. So you can see all these numbers here, right? And these numbers probably look scary and intimidating and weird. I mean, obviously, if you're familiar with hexadecimal, that's what this is. Because it's like there's letters in here like C and E and all that stuff, and D and F and A. So that's what this is, but even still, this may look really confusing, and it's easy to get lost in here. So, in fact, I already just got lost right now. Oh, here we go. Thanks for playing goodbye. Okay, so now I'm going to hit X right here, which is cross-reference. So what this is going to do is it's going to find out where in our program this string is used. So the string itself is going to be stored at this memory address, which is 0040302C, right? And now keep in mind that when I did our previous demonstrations with the slots, that's what these slots are, right? The slots I was talking about are just these address locations in memory, right? Now, as I said before, the numbers are far bigger than the numbers we were dealing with. I mean, this is a huge number. Let me show you how big this number is. If I go to calc, in fact, I could probably just do it from inside IDA, but I'm going to do it in calc to show you an alternate way to do this. So if you go to hex here and you type this thing in, so I'm going to, you don't even need to put the zeros, so I'll just type it in. So 40302C. Look how big that is. In that, so that's the actual number in decimal that we would read it as. That's a really big number. It's 4,206,636, and that's not even anywhere near how high the memory slots can go. So that just shows you right there how many spaces in memory we're talking about with RAM. So just keep that in mind. Okay, so I'm going to go ahead and jump to the area of the program now. I'm going to hit spacebar because it's going to make things a lot easier to read. This is really awesome. This thing's called graph mode, or this is called the I'm drawing a blank right now. It's basically a graph of the flow. Okay, so yeah, it's called the control flow graph. So basically, as I talked about before, a program is very linear. So I mentioned that in my last video when I put my finger up and I was showing you about how the thing follows instructions. So if we do jump back to this version right here one more time, we see that this is the program, right? The program is very linear. It's just the CPU has the instruction pointer, and it just goes down this code, and it just keeps going down this code and going down this code. And then what happens is sometimes it hits these jump instructions, like I was saying. So if it hits this right here, this basically means compare these compare this number with itself, and if it is not equal, then jump to this location. So it's going to skip, if that happens, it's going to skip all of this code right here, and it's going to go down here. Okay, so don't worry about the details of this because that's assembly language, and I'm not trying to teach assembly language in this particular series, but just know that there's a linear flow of the program. So once again, I'm going to go back to the graph here, and so this is main right here. So I'm going to rename this to main by hitting N and then Alt K. So as you can see here, this is starting to look a little bit more like our program because it's smaller, and that's how our program actually was, right? Our program was not a big program. This is much more manageable and easy to read here. So now in here, you can see how this told us this is char star, and you can see how the string here is puts. So when it says call puts, that's the thing that's writing it to the screen, right? So I wanted to show you this disassembly because I wanted to show you how the memory addresses actually look in a program, right? So like I was saying, these are the memory addresses right here of where the instructions are. So you can see how it says .text. So that's what I was saying when I was saying that the loader, it loads the program into memory, but it has to go through and figure out what goes in what section of memory. So it basically what it does is it allocates an entire huge block of memory with like let's just say it's 200 million different addresses of memory, which it may or may not be that much. It could be less, it could be more, but let's say it does that, right? So it might save it might give the text segment 25 million spots, and it might give other segments 5 million spots each, or something like this, right? That's one of the things it's doing. It's doing a lot of other things, but that's one of the things it's doing. So all of this, all of the actual program code, the instructions that you wrote, they end up in this text segment. And these are the addresses in the memory space of the text segment that got assigned for this particular program, right? Now, that's enough of this disassembly stuff, because that's all I want to do to explain here. So what I'm going to do now is I'm going to run it in a debugger. Or actually, I'll save that database. Why not? We can go back and open that up. I'll know where main is right away. So what I'm going to do now is I'm going to run the program in a debugger. And the debugger is called Ollie Debug. It's very popular, and all it's going to do is it's going to show us the actual layout of the program while the program's running, whereas IDA showed us the layout of the program as a file on disk. So remember what I was saying last time is when you download a file, it's on disk, and then when you run the file, it gets loaded into memory. It goes through the loader. The loader reads the file just like IDA did, and it figures things out, and then it places it in memory, which is what's going to be what Ollie is going to show us. So here we go. And once again, don't get overwhelmed because, oh, I got to run it as, I want to run it as administrator actually, so we can do stuff. Gotta love the permission stuff. Okay, so I'm gonna drag it in here, or maybe I have to open it. There we go. Okay, so now it's running inside of Ollie Debug, which, like I said, don't get overwhelmed because there's a lot of stuff that appears to be going on here. But what I want you to pay attention to here, though, is this stuff on the left, right? So check this out. There's a whole bunch of these memory address numbers again. So 77E17488D, 77E1748F. So check this out. I'm going to go to calc again. I'm going to put this in there, and you're going to see just how crazy these numbers get. Right, so look how big of a number this is. That's 2,011,264,141. So I wasn't joking when I said that these memory there's a ton of memory space and in RAM, and there is therefore a ton of different addresses to get to these different spaces in RAM. So as you can see, these instructions are now loaded in memory. They're active. This program is loaded in memory, but it's paused right now. So if I hit play, it's going to run the program, right? And you're probably familiar with some concepts like this. If you're already programming, especially in a higher level language, chances are you have used a debugger before, and this is just a debugger, but it's debugging the machine code rather than the higher level code that you've probably used with a debugger when you've been programming. So you can do step throughs, step overs, and all that stuff. You can put breakpoints down here. Like if I double click right here, it's turned red. Now we have a breakpoint, right? So this is not a tutorial of Ollie Debug though, but I just wanted to bring that up. So the addresses down here, let me just show you. Let me hit Alt M here, and I'm going to bring up this thing. This is called the memory map. So once again, probably looks super intimidating, probably looks really scary and ugly, but what's going on here is this is the entire address space of the program, and it's reflected in this memory map thing here, this window. Um, so we can see here that see the addresses they vary drastically. Like it starts at like 00004, and then it ends up going way up to like 748 and all this stuff. So these are all the different segments that the loader has basically set aside in the computer's memory for this particular program. And so that's what I wanted to show you guys, right? So this is it in action here. This is like, for example, the PE header is the header of that's what the loader reads to figure out how to place everything in memory when the program loads. So notice that that's right up here at the beginning. And then after it reads the PE header, it figures out how much space it needs to allocate in memory for the program's code, how much space it needs to allocate in memory for the program's data, which is like the variables and stuff like this, the read-only data, and so on and so forth. And I don't want to go too far into this in this particular lesson, but I think I've rambled enough. But that's what I wanted to show you guys in this lesson was how the memory actually did get loaded and how it actually looked rather than just using the silly parking spaces slots and 1 2 3 4 5 6 stuff. But it's the same thing though. You can tell this is the same thing. It's just instead of 1 2 3 4 5 6, it's like 2,568,344 expressed in hexadecimal because hexadecimal makes it much easier to write a big number. That's all it is though. That's literally all it is. Like this memory, that's all memory is. It's just slots. That's it, right? And I don't care if this is holding code, if it's holding data. I don't care if this is the stack or the heap, which we're going to talk about in the next video. But it's still all the same thing. It's still all in RAM. The RAM has no concept of that stuff. In other words, you don't go to the store and buy more stack RAM or more heap RAM for your computer. It doesn't. That is a memory management concept that we're using. It's like if you buy storage space at a storage yard, and you say, okay, I'm gonna split this storage space in half, and the right side here, when you walk in, all the stuff on the right, we're gonna throw it in a heap, and all the stuff on the left side of the storage unit, we're gonna stack nicely on a shelf. That doesn't mean that like the storage unit changes, right? So that's a concept that I'm going to go deeper into in the next video. So thanks for watching, and I hope you have a great day. Take care.